Let's now turn to a two-dimensional example of the use of finite element method. We are going to use this unit square as a omega. We are considering the Dirichlet problem, and the value of lambda is, for simplicity, equal to 1. We recall this bilinear form, which should be equal to L of V for all V elementi in this Sobolev space W0, where A is given by this integral. Note that the gradient of U can be written by this vector, or it is in fact this vector in R2. So in the first component we have the partial derivative of U with respect to x1, and in the second component we have the partial derivative of U with respect to x2. Similarly, we have the gradient of V equal to this vector. And when we take the scalar product of these two vectors, we obtain the first component of this vector multiplied with this vector plus the component of this vector multiplied with this vector. So we obtain this integrand. And since lambda is equal to 1 for simplicity over all of omega, we obtain the integral. This omega is now divided into triangles. And let's show how this can be done. We are dividing it like this, and we have several node points, capital N node points in the x direction, and also in the y direction. We note here that the distance here is equal to, we call it h, which is this maximum diameter which we refer to the previous lecture concerning, and it's, as you can see, equal to 1 divided by n plus 1. What is this shaded area? It is the support of the ith basis function. This basis function equals 1 in this node point. It's linear in each of these triangles, and it's 0 on the boundary of the support here. Note that the support of a function is defined as the set where the function is different from 0. So this basis vector is equal to 0 on all over omega except for this shaded area. Let's just mention that this basis function can be considered as some kind of tenth function. In here at the node point we have the value of it equal to 1, and it's you can imagine that you have some tenth here where each of these walls are linear. Since the function is linear here, the partial derivatives of this basis function is equal to some constant value in each of these triangles. So this was a general scheme. If we have n equal to 3, then we get this triangulation. In this case, the length here is equal to 1 over 4. Here I have illustrated these basis functions. You see here at this node point, the length is assumed to be 1, or the height of this basing function is assumed to be 1, and you can see that it's some kind of tent function, so it's linear on all these triangles. Here you see the support of the basis function v1, which is 1 in the this node point, and you see that this function is 0 all over this that, except for the support area where it may be different from 0. So in each of these triangles, the gradient or the derivatives are has some value, may be different from 0, and out here the value of the partial derivatives are equal to 0. Let's now consider the support area for the basis function v9. So this area looks like this, and here you see the value of the stiffness matrix A, V1, V9. So this is the stiffness element capital A19. We know that this is a pairing of the first basis vector with the 9th basis vector, and we just use this expression for the bilinear form. Now we see that this support area are disjoint, so they don't intersect at any point. So when the partial derivative of v1 with respect to x1, for example, is different from 0, this will be equal to 0, and vice versa. So we can conclude, and same for the partial derivatives in the x2 direction. So we can conclude that this integral must be equal to 0. The same happens for the pairing of v1 with v8. These two supports are also disjoint. So this stiffness element must be equal to 0. However, the pairing of v1 with v5 is different. Now you see that the support of the basis function v5 intersects with the support of our basis function v1, and the support area is this area, which we have illustrated by this square and this color. So what we have to do is to calculate the partial derivatives in both these triangles and find the value of them in both triangles, and take the integral over this area and find the values. Similarly, the pairing of v1 with v4 makes us conclude the same, that we have some intersection in this area, which I have illustrated by this symbol and the same color. And we note that in this area it may be some integral which is the integral may be different from 0. We don't know if it is, but it's likely that it is, so we have to compute it.